using what's called contingency tables. Now, a contingency table is a way of displaying our data that helps make it simple to calculate not just probabilities, but actually conditional probabilities. Okay? So it's very, very easy to decide which ones are in one set but not the other, or one and the other, simply by looking at the contingency table. So this example right here is on speeding violations and drivers' use of cell phones. All right? It's fictional data. Word of warning, it's not real, but you can still get the basic picture from this. So suppose out of 755 total people that we're considering here, 25 people had a speeding violation and used their cell phone while they're driving. Okay? So I can find the probability that someone had a speeding violation and used the cell phone by taking 25 out of 755. Right? That would be that probability. That is a joint probability. It's the probability that both this and this happen. What's the probability that someone uses their cell phone while they're driving? Any ideas? Okay. So this row is the people who use their cell phone while they're driving. Some of them got a speeding violation. Some of them did not. In total, 305 did use their cell phone while driving. And that's out of 755 in the set. Sorry. Out of 755 in the set. So 305 out of 755 is the probability that a person uses their cell phone while driving. On the other hand, 450 out of 755 is the probability that they don't. And it's not an accident that those two things add up to 1 or to 100%. Again, that's the probability of our entire sample space because we're looking at those two disjoint events. They use their cell phone or they don't. So this is how this is organized. And it's very useful in terms of conditional probabilities because, for instance, if I want to find the probability a person had a speeding violation given that they use their cell phone. Well, that means I'm assuming that they are already in this first row, and I only need to compute the probability using the first row. So the probability of a speeding violation then would be 25 out of 305. Because I'm assuming they're in the first row already. That's the given part. I could also calculate the probability that they use their cell phone given that they had a speeding violation. Well, that means I'm assuming they're in this column. They had a speeding violation. And the probability they use the cell phone then is 25 out of 70. So contingency tables make that very simple. You just have to think very carefully about which piece is assumed, only focus on that row or that column, and then the probabilities are just right there. It's just writing the ratio of those two numbers. All right. So let's do a few quick examples. I'm going to write this down just so I don't miss it. Here's my table. I'll call C the cell phone and S speeding violation. S is a bad choice. V for speeding violation because S is the sample space, right? So let's see. C, not C, and then V, not V. And so 25. Total. 25, 280, 305, 45, 405, 450, 755. I should be able to add these, but I don't like doing that in my head, especially with an audience, and especially when there's a digital record of it. There we go. So this is the same contingency table. I'm just summarizing it a little bit cleaner. Now I have 4 questions I'd like us to answer. Let's find the probability that the driver is a cell phone user. from this table, how would I get that?
Add 25 and 280.
Okay, so cell phone users are the 305. And the total possibility, the total number of drivers in this entire collection is 755. So it's 305 out of 755. And I know that can be simplified, but I'm not going to worry about that for here. Okay? I believe that my open math is okay if you don't simplify those. But in cases where it would want you to, it usually will ask for a decimal value anyway. So I can compute that with a calculator and figure out what 305 out of 755 is. It's going to be a little less than a half, maybe 43, 44%.
40%?
Yeah?
40%?
40% is exactly 40%?
No.
But it's approximately.
Yeah.
Okay? That's fine. All right. Second question. What's the probability that the driver had no speeding violation? By the way, we also might write that as V complement. Right? What would that be?
685.
Out of 755. Excellent. All right, so that's going to be most of them. Right? 70 out of the 755 had speeding violation. It's more like 0.91-ish. Again, I'm just estimating, so plug it in the calculator to find the exact value. But that's the idea. I can read it off here and compare it to the total. All right. What's the probability I have a driver who did not have a speeding violation, so that's not V or V complement. I'm writing the other way this time. And was a cell phone user.
$280.
All right, that's not V is right here, C is right here, so this one entry is the people who satisfy these two things. 280 out of
755.
755. 7 times 40, 7 times almost 100. That's going to be about 0.4-ish. A little bit less, actually, more like 0.38. Again, calculated directly to find exactly. What's the probability the driver is a cell phone user or had no violation in the last year? A few different ways to calculate this. Okay. Well, the probability of the cell phone user is this row. All right, so that's 305. And the or, not V, as in this one extra box. Right? So it'd be 305 plus 405, which is 710. Out of 755. That's maybe 95%. Again, just an estimate. Okay. How else could I have gotten this? I can think of it as a Venn diagram, right? If I add the probability of C and the probability of V complement, or not V, together, that's almost the right answer, but I've double counted the place where they overlap. So I have to subtract away that part that was double counted. Well, that's actually the first three answers here. I can take the 305 plus the 685 and subtract the 280, which were counted twice. Right? If I add up the C's, I get these two pieces. If I add up the V's, I get these two pieces. And that's double counting this one piece. So I take 305 plus 685, that's 990. Subtract from that 280, it looks like 710. And sure enough, 710 out of 755 is the exact answer I expected to find. All right, great. Questions about that? That's what a contingency table will do for us. Okay. All right. So Venn diagrams, you've probably seen again the two set version. It's a way of organizing the counting of two sets, and so if we're using sets to represent the possible outcomes in our sample space, this is a great way to consider things like joint probability, or the probability that either event happens, the or probability, the inclusive probability. Okay. Again, this summarizes what happens with the addition rule, with that inclusion-exclusion idea. Sorry, coffee's catching up to me. We can also use it in terms of counting problems, and these are actually closely related to the equivalent ideas for probability. So I'm going to show you an example here with the counting problem. Suppose I'm looking at the enrollment on two different classes. One is a statistics class, and the other is a literature class. And I know that there's 35 students in the statistics class, and 30 in the literature class. Now suppose that when I look at that list of students, there's a total number of 55 unique students on that list. Well, what does that tell me? Take a guess. What do you think?
55 of them are in both?
Not necessarily. In fact, since only 35 are in statistics, it can be that 55 are in both. But 55 are total across the two. Specifically, there are some students in both classes. I don't know how many, but we can figure that out with a Venn diagram. And there are some students in one class but not the other, in both directions. So how do I figure out which is which? Well, here's what I'm going to do. I'm going to draw a Venn diagram. I'm going to let S stand for the statistics students, and L stand for the literature students. And so students who are in this group are in statistics, but not in literature. Students in this group are in literature, but not statistics. And students right here in the middle are in both. Okay. Now what do I know? I know that the number of students, put it this way, equals 55. I know that the number in S, that includes both of these pieces, is 35. And the number in L is 30. Well, if I thought that these were two mutually exclusive events, which, by the way, as a Venn diagram looks like this, right? They have no overlap. If one happens, the other can't, right? If I thought that these two things were mutually exclusive, that is, there's no statistics students who are also in literature, then the total number of students would be 30 plus 35. Right? I have 30 on this side, I guess, and 35 on this side for a total of 65. But that doesn't match up. So there has to be an overlap, and in fact, I can tell how much they overlap by. How much?
10?
Yeah. If I just add these two things together, I would overcount by 10. That must be the overlap, because I counted those students twice. So, the number in S and L is 30 plus 35 minus 55, right? It's the number in the first group plus the number in the second group minus the number that are in both. Or excuse me, the total between them. Okay. And so that must be 10. And then what I like to do is I like to write this in. There's 10 here in the middle. And if there are 30 in literature, 10 of whom are also taking statistics, how many are in literature but not statistics? Well, I need to know a number here that when I add it to 10 gives me the total in literature.
20.
All right, it's going to be 20 here. Because when I take the 20 and 10 together, I get the 30 that are in literature. Let's do the same thing for statistics. I've already counted for 10 of those students who are in both classes. And if there's 35 total, how many are in just statistics? Louder? 25, good. Okay. Now if I did it correctly, I should be able to add up these three pieces and get the total number of students across both groups. 25 plus 10 is 35, plus 20 is 55. That's the number of students I expected. So a Venn diagram will help you with counting those kinds of things, and this is particularly helpful when they're equally likely. If I were to ask you the probability of choosing a student who is in both statistics and literature, you would say it is 10 out of 55, and you could compute that using this same set of ideas. Questions about Venn diagrams? We won't do too much more with these because these inclusion and exclusion problems are basically all we really need to be able to do with those. That's to find the or probabilities, the probability that A or B happens.